Hey guys, welcome to the Unit 9, the last unit of the APES curriculum. Admit it, you're going to be sad when this course is over. But first, you got to get through that test, right? We got one more unit in front of us, and we're going to start off this last unit on global change with stratospheric ozone depletion. And I'll say that a lot of people, lay people who don't really know a whole lot about it, they confuse this with another global atmospheric problem, which is global warming. They have nothing to do with each other. Okay, that's a hard aniello on that. The two things are very different from each other. And so let's just jump into stratospheric ozone depletion. So first of all, we're talking about ozone in the stratosphere. Ozone in the stratosphere is a good thing. Tropospheric ozone down at ground level is a bad thing, or that's made by photochemical smog and it attacks our lungs. But stratospheric ozone, which is up in the stratosphere, maybe 20 kilometers over our heads, that's some good stuff. So let's just look at what it does and why it's important. Okay, so start off, we have to understand that the surface of the sun gives off light, and basically the faster the atoms are shaking, the higher energy light they give off. So the sun gives off, there's some slow moving atoms up there, and they only give off what we call infrared light. But the vast majority of the atoms on the surface of the sun are wiggling at speeds that are going to give off visible lights, everything from red, orange, yellow, green, blue, indigo, and violet, which our eyes can see. Okay, the reason we evolved to see them is because that's what the sun gives off. But the sun also gives off some energies of light that are beyond or above violet, so we call that ultraviolet. And this is really what the story of ozone depletion is all about, this ultraviolet light that exists beyond what our eyes can see. It's there, we can't feel it, but it interacts with us in negative ways, and so we need to come to understand it. Now, we can further divide that UV part of the spectrum here into three different regions, okay? So you can actually go to four, but we'll just talk about three of them, okay? So we can divide it into what we call UVC, UVB, and UVA. All right, so UVC is really energetic light, okay? So the highest energetic light that the sun is giving off. And it turns out, thank God, none of it reaches the ground, because if it did, we'd be in a world of hurt, okay? We die, okay? You just couldn't have life. So in that sense, if there wasn't an atmosphere, we'd be exposed to all this stuff. It'd be bad. Okay. Now, um, a lot of the light that reaches the ground is a lot of the ultraviolet light is UVA. So that's the lower energy UV. All right, and this goes through the atmosphere unimpeded. But a small amount, about 5% of the UV light that reaches the ground, is what we call UVB. It's more energetic than UVA, but less energetic than UVC. UVB is the bad stuff. Okay, UVB is the stuff that causes skin cancer and other problems. So that's what we need to understand, is the role that the ozone layer plays in limiting the amount of UVB that gets to the ground. Because some of it does, you know, but how much it gets down here has to do with how much ozone is in the atmosphere. But before we get to that, let's just talk about the difference between UVA and UVB. UVA is more penetrating. It goes deeper into our bodies than UVB. But fortunately, it doesn't have enough energy to disrupt the DNA in our cells. And as a consequence, it doesn't result in mutations, so it doesn't result in cancers. It does cause some changes in our collagen and things like that. So it causes skin to become darker. In some places in the world, like in America, lots of people lay out in the sun because they want to get darker. I notice here a lot of people cover up because they don't want to be darker, which is a lot healthier, because and also, by the way, that causes aging, like the wrinkles and the spots that I've got all over my hands. This age spots. Those are all result of UVA. UVB is the bad stuff, which I've also had a problem with. I've had a number of skin cancers removed. Thank goodness, none of them have been ones that are uh, life-threatening. They don't metastasize, no melanomas. But what happens is UVB, which doesn't penetrate as deep, it does damage DNA, which leads to mutations, which lead to cancers. So, and not only does it lead to cancers, but also when it gets into our eyes, it can change the proteins that the in the tissues that make up the lens of our eyes. And over time, our eyes tend to get cloudy. So as people get older, they get a condition called cataracts. So a lot of people, by the time they get to my age, they have to have their lenses of their eyes removed because they start clouding over. A lot of people I know have had that happen. So what's protecting us from this UVB stuff? Okay, so remember, none of the UVC gets to the ground. All of the UVA, and it's none of the UVC, all of the UVA is that UVB that sometimes does, sometimes doesn't. So here's what's going on. So we have O2 molecules in the atmosphere, and ozone is O3, but it's not as stable as O2. So ozone is this kind of delicate molecule that helps protect us. Where does it come from? Well, it turns out it comes from ultraviolet light, mostly from UVC light. Okay, that very high energy. None of it gets to the ground, right? Because what happens is when UVC light comes in, this high energy light, it hits an O2 molecule. We'll call it diatomic oxygen molecule. Okay, it's two atoms, diatomic O2. What happens is it hits it and it has enough energy to break it apart into two monatomic oxygen atoms. All right, so what was a molecule is now two in these atoms. And these atoms are very reactive. And what will happen is they'll meet up with another O2 and form into O3. So this one found one molecule of O2 and became O3. This one found another one of O2 and became O3. So ozone, which is the O3 allotrope or triatomic, if you will, oxygen molecules, it's formed when UVC light breaks up an O2 molecule, and then those broken parts reassemble as O3. All right, and now we have ozone. So ozone is made, ironically, by ultraviolet light, mostly by UVC light. Now, where this happens, it tends to happen in between the troposphere and the mesosphere, in the stratosphere. Basically, mostly say between 10 to 50 kilometers up. Okay, and in this region there is a temperature inversion that occurs because as this energy from the sun doesn't make it to the ground, that energy can't go away. So what happens is it gets warm. Okay, now UVA light, it just passes right through. So UVA light passes through oxygen, it passes through O2, and it also passes through O3. That's why all of it gets to the ground, because neither O2 neither O2 nor O3 block UVA. It also passes through clouds and glass and other things like that. But now let's talk about UVB. Now, what happens to the UVB light is this. So it can also, like UVA, can go through clouds, but here's what happens. It passes through O2 just fine. But when it hits an O3, an ozone molecule, look what happens. This UVB light has enough energy to break off that loosely held third oxygen atom. So it breaks it apart. The energy here was used to break this apart. So this UVB photon is not making it to the ground. That's one less that might give me cancer, right? And afterwards, what happens? Well, now I've got a diatomic O2 and a monatomic O. Well, guess what? This is going to find one of these and form one of these again. So basically, the ozone absorbs the light, the UVB light breaks apart and then reforms as ozone. So this is this constant cycle of breaking and reforming ozone. And as long as that happens, very little of that UVB light is going to make it to the ground where it's going to harm people or other organisms. So here's a little graphic to help you see that. So all of the UVC light is going to be absorbed, making ozone. All of the UVA light is going to pass right through it, not a problem. It's the UVB light that gets absorbed by ozone, but there's not as much. There's not so much ozone that it doesn't all get absorbed. So some of it does make it to the ground. Here are the problems. Okay, so UVA is really not a problem. It's what they use in tanning beds. It's people worry about it a little bit, but it's really not that bad. UVB is, because remember, UVB has enough energy to damage DNA, which causes mutations, which leads to things like cancer. Now, let's just talk about some of the different things it can do. Okay, so skin cancers. All right, that's one. Now, some skin cancers like squamish or basal cell carcinoma, not a problem for people, but melanoma kills people. All right, I've had several friends die from it. All right, it causes cataracts, as I said. It denatures the proteins in our eyes. It can also lead to reduced photosynthesis in terrestrial plants and some aquatic plants that are near the surface, including planktonic organisms. And so basically it reduces food production, and that food production can affect whole ecosystems, because we're not just talking about human crops, we're talking about just, productivity in general goes down in some species and not others. So it alters which organisms become dominant in an ecosystem. It changes the amount of life that can be supported. It changes the base of the food pyramid, so that the total population goes down if you lose or if you lose the base of it, if you lose photosynthesis. Another thing it can do is it can also, research has shown, change the rate at which carbon dioxide gets back into the air from plants decomposing. Okay, plant matter decomposing. It aids in that process. Now, what causes ozone depletion? Why is there a problem with it? So what I've described so far is just this natural process, right? But it's getting worse, right? Well, it was getting worse. It's getting better now, but it was getting worse. And here's why. I really want you to zero in now on how ozone depletion occurs. So basically, people produce certain compounds that are anthropogenic chemicals that we produce. Some of them get up into the stratosphere, and when they're up there, they catalyze reactions in which O3 is broken down back into O2. Now, that happens naturally all the time by absorbing UVB light. But what happens is these chemicals do it, and so there's less ozone in the atmosphere. There's less O3 up there, so more UVB gets down here, and that's a problem. Now, most of these substances that do this, we call them ozone depleting substances, or ODSs, okay? Most of them are carbon compounds that contain halogens. So if you remember, halogens is that row 7 on the periodic table, or row 17, depending on which kind of periodic table you use. And so we're talking about chlorine, fluorine, bromine, not so much iodine, all right? Now, a lot of these things, they were designed in the 1950s, like after World War II, as these miracle things, because they had low toxicity, and they had the ability to do a lot of useful things. So they could be used for propellants, for like aerosol sprays. They were useful as refrigerants. So like you need a gas to compress and expand in order to make a refrigerator or an air conditioner work. They were used for as fire extinguishing chemicals, as dry cleaning products. So they had lots and lots of uses, but they all had the same sort of thing in common. They contain carbon, either 1, 2, or 3 carbons, and they contain chlorine, and they often contain fluorine, and again, sometimes bromine. And so there's a number of them here. They're listed here. Now, all of these things here have been found to, when they get into the stratosphere, disrupt the formation of ozone. So let's just see. Okay, well, here it is. Okay, so I just did this, so I'm going to go on. Okay, they're also used for making like styrofoam. I should point that out too. Okay, so let's look at how that works. All right. So when an ozone destroying substance gets into, or I guess it's not destroying, it's ozone depleting substance gets into the stratosphere, here's what happens. Okay, so here is a chlorofluorocarbon. Okay, and what happens is UVB light from the sun is going to hit this and break one of the bonds to these chlorines. And now I have this free radical, we call it, this chlorine, that is now drifting around, and it's monatomic chlorine, and that's very, very, very electronegative. And so it has the ability to bend and break these ozone molecules. So basically, we put this stuff in the atmosphere. We were using it, say, as a propellant. Whoops. There's Rob Paul. Hang on a second. Hey, you ready to go? Okay, I'm wrapping up a screencast, so when you come on down, I might still be talking. Okay, I'll try to wrap it up. Okay, all right, bye. I give them right home every day. Okay, so then what happens? Okay, well, this chlorine, now watch this, okay? So this monatomic chlorine in the atmosphere, here's what happens. You ready? So this chlorine, when it finds an O3, it will basically react with it, forming ClO and O2. Okay, so in other words, this is very electronegative. It attracts one that loosely held oxygen that sort of got added on at the end, comes over here. All right, now look, no ozone, mom. Okay, but wait, if that was the only way it happened, it'd be fine, because it would get the chlorine would get used up, but it doesn't get used up. It's a catalyst. Remember, a catalyst doesn't get used up, because look what happens next. Now, UV light will come in, UVC light will break up another oxygen, forming these ones here. Now, normally what would happen is one of these would drift down here, join with another O2, forming an ozone. That's what's supposed to happen. But instead, what happens is, instead of this one meeting this guy here, it meets this guy over here. So basically, this plus a monatomic oxygen, right, ends up producing O2 and Cl. And look, now I'm back to where I started. And this process just goes on and on and on. One of these in the atmosphere, when this happens to it, will oversee the destruction of hundreds of thousands, sometimes tens of millions of ozone atoms. This chlorine just drifts around up there, and it's very light, so it's not likely to fall down. It can take decades and decades for it to finally like get stuck to something that's going to make it come out of the atmosphere. That's the problem with this stuff. So right after World War II, people started making these CFCs, and that's I'm just going to use that as an example. There's other uh, uh, there's other of these ozone depleting substances, but we'll just worry about CFCs because they're the main ones. Okay. So what happened was, sorry, I had to do a screenshot from a YouTube video because I just couldn't find a good graph of this. I was too lazy to make my own. So what we find is that man, it skyrocketed up. Oh man, look at that! We just made more and more and more of this stuff, and it just leaked into the stratosphere. Well, what happens then? Here's ozone. So ozone, which is late measure these things called Dobson units, which like I don't know if you need to know this. I know I've looked. You don't need to know about Dobson units. Never mind. But what we found is the ozone, the amount of ozone in the atmosphere started coming down as the CFCs were going up. All right, and it's because they were destroying ozone at a rate faster than which it could replace itself. Well, what happened then? Well, then what happened was since there's less ozone overhead, there's more UVB light reaching the ground. So here's a graph of UVB. Now this is done by different latitudes, okay? And we'll talk about that in a little bit. But basically you can see is from the 60s to 70s to the 80s, all the way up to 2000, the amount of ultraviolet light reaching the ground went up. But now look at it. Things are getting better now because this story is one of the few ones that has a happy ending. I swear it does, okay? And we expect things to get much better by the end of this century. All right. Now, what happened? Turns out in 1987, there was a thing called the Montreal Protocol, and all the nations in the world, with few exceptions, signed on to it. And they said, look, we're going to stop making these ozone depleting substances. We're just not going to use it. We're going to find something else to use instead. And basically 190 countries eventually signed on to it. And look what happened. The amount that we produced in terms of CFCs and other ozone depleting substances went way down. And they dropped by like 95%. So that, I mean, it worked. We found other things we could use. So we said, look, and by the way, as that happened, then what happened is the amount of ozone in the atmosphere starts to come back up, right? So as you stop making these CFCs, the ozone is going to come back up, and it's already started. The process, look, we've already hit bottom. We've already started to come back. So like this isn't just being optimistic. We're already at this part of the curve here. So we see this process happening, and the science is there to say this is how it's going to play out. There's no reason to think otherwise. So one of the reasons it was successful is because people just said, look, we can find something else to do. And they did. They said, look, instead of using chlorofluorocarbons or CFCs, we can use instead these HFCs or hydrofluorocarbons or hydrochlorofluorocarbons. Okay, but we're putting this hydrogen in the molecule, and it makes it a little bit less effective at the job it was designed to do, in terms of refrigeration or foam production or whatever. But it doesn't destroy the ozone. And that's a great thing, right? Now, there is one drawback. Isn't there always a drawback? The drawback is this. These things are often really bad in terms of their ability to cause global warming. So when we measure global warming, we'll talk about this in a subsequent screencast. We call it the global warming potential, or the GWP. So the way you think of it this way, CO2, the arch enemy of the world, right? Carbon dioxide is assigned a GWP, a global warming potential of 1, okay? So what we did is we look at these things here, these HFCs rather, look at their global warming potentials. They're enormous. So what we're saying, let's just look at this first one here. So pentafluoroethane, which is this chemical here, one molecule of that has the same global warming potential as 3,500 molecules of CO2. Now you might think, well, then let's not use them. But here's the thing. We dump so much carbon dioxide in the atmosphere every day. We are not dumping tons of it. It just took a little bit of that stuff getting in the atmosphere to break loose. And remember, because it just stays up there and keeps catalyzing these reactions. These things don't do that. So it's not like we're not putting so much in there. I assure you, we're putting so little in there that this is really not something we should be worrying about. It's doing much more good than it is doing harm. Now, a lot has been made about the Antarctic ozone hole, which, by the way, there's an Antarctic ozone hole. There really isn't much of an Arctic ozone hole. It just has to do with the fact that climatic conditions, due to the sort of isolated nature of Antarctica, allow the temperatures to get much colder there in the wintertime, our summer, their winter, and then they do in the Arctic. And so there is an Antarctic ozone hole that forms, but there really isn't much of an Arctic one. Okay, so basically what we find is that during the Antarctic spring, which is October here, a large hole opens up. So like we just look at the level of ozone, it just really plummets quite low. It's exceedingly low pretty much every spring in this region around Antarctica. And that causes a lot of problems. Like so the ecosystems here are definitely affected, right? It affects the plankton, the whole food web as a result of that. All right, but let's just see, why would that happen? Why there? It has to do with these beautiful clouds that people have loved to take pictures of for years. So basically, in Antarctica, the stratosphere gets so cold in the winter that these stratospheric clouds called polar stratospheric clouds form. And basically, it is the formation and dissipation of these ice crystals that make up these clouds that is responsible for that just overwhelmingly deep hole in the ozone that forms. So here's how it works. During the Antarctic winter, which is our summer, so say May through September, the air in the stratosphere over the South Pole gets super, super cold. We're talking like negative 80 C. And it can do that because there's this thing called the South Polar Vortex that sort of keeps any air from moving into the area. And now the sun's not shining there, so it gets really colder, colder, colder. And even though there's not much water vapor in the stratosphere, what little is there is going to form these little tiny ice crystals. And what happens is these little tiny ice crystals tend to accumulate pollutants that people put in the air that have chlorine in them, all right? And these aren't necessarily always CFCs, but there's pollutants that have chlorine in them, and they start to adhere to the surface of the ice. Now, what happens is, as these chemicals, and notice this isn't a CFC we're showing here, but it would work with that as well. What happens is these chemicals start sticking to the surface of the ice crystals, and they react with other things, that other chemicals that are in the atmosphere. So, and then what happens? The chemical reactions happen on the surface of these ice crystals during the dark months of winter. And so what happens is an accumulation of diatomic chlorine starts to build up as a result of the reactions occurring on the surface of these ice crystals in these polar stratospheric clouds. But it's really dark, it's cold, and we just have this chlorine. Now, this chlorine, diatomic chlorine, does not destroy ozone, but monatomic does. And so here's what happens. In the winter, a lot of this builds up from these chemical reactions that are happening on the surface of these ice crystals. Spring comes, and all of a sudden the sun comes up. Remember, the sun hasn't shined all winter, from the equinox, from the September equinox to the March equinox. There's no sunshine there. But man, March 21 comes, the sun comes up, and all of a sudden the UV light from the sun hits these chlorine molecules and breaks them apart. Now I've got chlorine, and remember what happens? Chlorine reacts with ozone, forming this, and then the cycle keeps completing. We go right back to this. So that's why it happens. We get this big buildup of Cl2 during the winter from these reactions on the ice. In the spring, light breaks them apart and triggers this problem. But let's just take a moment to have a little victory lap here. So look what happened. Because of the Montreal Protocol, which got signed here, right, like around here, what happened was the ozone in the world was just plummeting, but we stopped putting CFCs in the atmosphere and other ozone destroying. I keep saying destroying, ozone depleting substances. But what happened is slowly they started coming out of the atmosphere. Because remember, they catalyzed for a long time. And now here we are, and we're starting to move back up. And when we run our models, we see we should make our way all the way back up here. So that ozone hole still forms every winter, but we feel like by the end of the century, it should almost be completely healed and the problem will be completely fixed. So listen, a happy story for once, right? It shows what happens when people use science to identify a problem, when we look around and use engineering to find solutions to that problem, and as a global community, we decide that we are going to act in the global good. This can happen. It happened with the Montreal Protocol for ozone depleting substances. It can happen again for carbon dioxide. It's just a little bit harder to do it than it was with this, but it can still be done. All right, thanks for watching. Sorry this took so long. Let's see.